Welcome back, everyone. Our goal today is to continue to talk about sizes of infinite sets. And remember the hierarchy that we talked about last time, where we have finite sets, and we understand these pretty well, at least as far as cardinality goes. That is one box. Then further down the hierarchy, we have sets whose size is aleph naught. So this includes, for example, the positive integers, but also includes, for example, the even integers or all the integers. And then further down the line from that, we have things which are of size aleph c, and aleph c is the size of the real line. And we've proven over the past videos that really the sets that are in this bucket, the aleph c bucket, they're really larger than the sets that are in the aleph naught bucket. Now, there are more buckets, but almost everything you've ever thought about as a set is in one of these three buckets. That is, it's finite, in which case it's in some sort of sub-bucket that says the exact number of elements it has, or it has the same size as the positive integers, or it has the same size as R, and we've named those things aleph 0 and aleph c. And so today what I want to do is to sort some of the sets we have not talked about yet into their appropriate bucket. Now, if you think back to our definition, what is it I'm really going to have to prove that something belongs in the aleph naught bucket? Well, I'm going to need to prove that it has the same size as something in the aleph naught bucket, which means I'm going to have to prove that, for example, there exists a bijection between that set and the positive integers. Or, if I want to prove that something is in the aleph c bucket, I have to prove that there exists a bijection between that thing and the real numbers. Now, it turns out, as you've probably already seen, showing that there's a bijection between a complicated set and one of these sets is, well, complicated. And we would like to avoid that as much as possible. So the first thing I want to do today is show you a way we can get around having to think about showing that there's a bijection between two sets in order to show that the two sets have the same size. And the way we're going to do that is going to be to use the thing we called in the last video the Cantor-Bernstein theorem. So this lets us talk about the cardinalities of two sets A and B, and it really had two parts. The first part was the one we proved, which said that given our definitions of the cardinality of A and the cardinality of B, and what it means for the cardinality of A to be greater than or equal or less than or equal to the cardinality of B, then we have that the cardinality of A is less than or equal to the cardinality of B if and only if the cardinality of B is greater than or equal to the cardinality of A. Now, just a quick reminder, this looks silly because it looks like I'm just manipulating notation, but we actually defined these two things in very different ways. Namely, we defined this as the existence of a one-to-one function from A to B, and we defined this as the existence of an onto function from B to A. So even though this looks obvious from the notation, it turned out it wasn't at all obvious. The other piece, which also looks like I'm just manipulating notation, was that if the cardinality of A is less than or equal to the cardinality of B, and also the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A and the cardinality of B are equal. Again, this looks obvious if you just believe this notation works the way you want it to, but basically the theorem is, yes, this notation works the way you want it to. And in particular, what this does is this lets you show, for example, that there is a one-to-one function from A to B, and a one-to-one function from B to A, and then conclude that there's a bijection between A and B. So what am I buying here? I'm buying myself an exchange. Instead of showing the size of A is equal to the size of B by writing down a bijection between A and B, I get to trade that task away for instead two simpler tasks, namely giving a one-to-one function from A to B, and a one-to-one function from B to A. And the first part of the theorem here lets me trade either of these two pieces, which concern something about a one-to-one function, for something about an onto function. Namely, because the size of A is less than or equal to the size of B, if and only if the size of B is greater than or equal to the size of A, I could, instead of showing that there's a one-to-one function from A to B, show that there's an onto function from B to A. So there are all kinds of combinations that between these two results will get me that two sets have the same cardinality without ever having to actually write down a bijection, which is definitely what I want. So here's an example where the thing it says is kind of obvious. Namely, if I start with this set, which remember, we've shown previously that the open interval 0, 1 is equinumerous with the real numbers. We used tangent and inverse tangent to do that, but that was in, I think, the first video on cardinality. But if I start with this horribly infinite set and I throw in two elements, 0 and 1, that's the only difference between these two things, then it stays the same size. It doesn't get bigger or whatever. And that should, I hope, be pretty intuitive if you believe that the open interval 0, 1 and all of the real numbers have the same cardinality. Then certainly throwing in two things shouldn't be any worse than throwing in all the other real numbers. Now, as intuitive as this statement is, this question appeared on the homework where I asked you to do it by showing an explicit bijection, and that turns out to actually be quite annoying, and so I've only actually made you do something like that once. But on the homework, you have to actually show me that there's a bijection between these two things by writing down a bijection. But if I'm allowing the use of the Cantor-Bernstein theorem, we can do this more easily. As we've often seen here, if I'm going to prove this by Cantor-Bernstein, I'm going to need to prove two pieces. That the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A. So I should state that's what I'm going to do, and then I should do each of those pieces. So the first part is going to be the size of A is less than or equal to the size of B part. In order to show that the size of A is less than or equal to the size of B, remember, I have to show a one-to-one function from A to B, or an onto function from B to A, because remember, those two things are the same by the first part of Cantor-Bernstein. However, in this instance, I think it is much easier to write down a one-to-one function from A to B. Namely, since the open interval 0, 1 is a subset of the closed interval 0, 1, I can just send every element to itself. And so once I do that, certainly f of x equals f of y implies x equals y. Because literally that's all f does for all x and y in A. So this is sort of visibly one-to-one. That was the easier half. Now I need to show you that the size of B is less than or equal to the size of A. And so I have two options here. I can show you a one-to-one function from B to A, or I can show you an onto function from A to B. Now, in this instance, I think both of those are things that we're capable of coming up with, so we can use whichever one we like. I'm going to take the linear function from B to A that takes x to a quarter plus 1/2 x. Note this function's increasing, because this is just a line, so it's one-to-one. And why is this really a function? That's actually the thing that actually takes a second more to see. That is, why does everything I put into B give me back something in A? But actually, if you think about it, the image of G is visibly just the closed interval 1/4 to 3/4, which fits neatly inside the open interval 0, 1. So I get here a legitimate one-to-one function, and so I've shown that the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A. And so, by Cantor-Bernstein, the size of A and the size of B are equal. So here's the point. It's much easier to write down two different functions that are both one-to-one, one in each direction, than it is to write down a single function that's a bijection between these two. But because of the Cantor-Bernstein theorem, we know those two things are equivalent, so this is good enough. Now, in the case we just did, I think it was fairly clear what the answer was going to be. Namely, I think we could probably have guessed that these two things were going to have the same cardinality. What I want to look at now, though, is something where I think it's less clear. So here what I'm going to do is I'm going to ask about the cardinality of the Cartesian product of the positive integers with the positive integers. One way to visualize this is to think about this set living in R2 And so then we have this point that's 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, and so on down the line like this. But going forever in both this direction and this direction. So, what do you think? Do you think this is going to have the same cardinality as the positive integers? Do you think it's going to have the same cardinality as the cardinality of the real numbers? Do you think it's going to be some other thing? One thing you might notice is that if you pick your favorite column, just that column by itself already has as many elements in it as the positive integers, right? This is certainly Aleph not points. Why? Because I could say, okay, there's the first one, the second one, the third one, the fourth one, and so on down the line. And if I think about how big z plus cross z plus is, well, there's lots more points. In fact, there's far more points that I have not counted than there are points that I have counted. So I might be inclined to think, okay, probably this thing has bigger cardinality than Aleph naught. That is, I think probably this thing has bigger cardinality than the positive integers. And I think that's definitely what you should think, but it's not true. This thing ends up having the same cardinality as the positive integers. So to prove this claim, we need to again use Cantor-Bernstein. Okay, so I'll go ahead and let A be the positive integers, B be the positive integers, cross the positive integers. So in other words, I need to know that the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A. So let's do the size of A is less than or equal to the size of B first. I think this is the easier direction, and in fact, if you look at my picture over here, I kind of already showed you how to do it, which is to namely take the function from A to B. So here I'm taking an integer to a pair of integers, and I will take the integer n, and I will map it to, and the thing I put over here was 4, n. Namely, when I did this, I said, okay, I'm going to take just the fourth column, and so these are all the ones with x coordinate 4, and so that'd be 4, 1, 4, 2, 4, 3, 4, 4, and so on. This function is definitely 1-to-1. Now, you've probably noticed a lot of the times when we prove something that involves two directions, there's sort of an easy direction and a hard direction. This was definitely the easy direction. So here's the harder direction. I need to show you that this ostensibly larger set is in fact actually at most as large as the ostensibly smaller set. And remember, there's two things I could choose to do. I could give you a 1-to-1 function from B to A, or an onto function from A to B. Now, I'll later give you the onto function from A to B, because I'll actually show you how to write down a bijection here. But for now, I want to emphasize I don't need to write down a bijection. I can just write down a 1-to-1 function. And here is a 1-to-1 function, although this one's a little trickier to come up with than the 1-to-1 functions we've written down so far. So I'm going to take the ordered pair, m, n, and I am going to send it to the integer 2 to the m times 3 to the n. Now, at first, it might not be clear why this is going to end up being 1-to-1. That is, why is it the case that if g of mn equals g of xy, that m and n is equal to xy? Now, I'm going to go ahead and name this thing that both g of xy and g of mn is. Namely, I'm going to call it capital N, which is maybe slightly confusing, but I'm calling it capital N because I want to emphasize it's an integer. So I want to show you by looking at this integer that in fact x, y and m, n had to be equal. So what do we know about positive integers? Well, one thing we know about positive integers is that they have a prime factorization. So I am going to write n as a product of primes. And there's actually two ways to do that, owing to the fact that n is both g of m, n, and g of x, y. And so actually, one way to write n as a product of primes is as 2 to the m times 3 to the n. But another way to write n as a product of primes is as 2 to the x times 3 to the y. But, and here's where the magic happens, prime factorizations are unique. there is only one way to factor any positive integer as a product of primes. So in fact, these two ostensibly different ways of factoring n must in fact be the same. So, by unique factorization of integers, m is equal to x and n is equal to y. So, what have we shown? We've shown that this function g is a one-to-one function from z plus cross z plus to z plus. So, size of A is less than or equal to size of B, size of B is less than or equal to size of A. By Cantor-Bernstein, these two sets have the same size. Now, this is a little mind-bending, because, again, it really looks like z plus cross z plus should be vastly larger than z plus. In fact, it seems like, if this even makes sense, it should be sort of like infinity times as large, because every one of the infinitely many columns here is just as large as z plus itself. And yet, because of this sort of hotelish way we could sort of slide around rooms in an infinite hotel, we actually ended up showing that in fact I could squeeze every ordered pair of positive integers into the positive integers. And, in fact, if you look at our function, we did it with lots of room to spare. Because the image of this function that we wrote down from z plus cross z plus to z plus is actually just the numbers that happen to be a power of 2 times a power of 3. Most integers are not a power of 2 times a power of 3. In fact, there's tons of room left. So, the moral of the story is that as much as it might seem paradoxical, z plus cross z plus also lives in this Aleph naught box. Continuing on our list of sets that we haven't yet addressed, let's think about the rational numbers. And in this case, I'm just going to think about the positive rational numbers. Like in the previous question, I think it's natural to think of how the positive rational numbers compare to the positive integers. So if I look at the real line, or the positive part of the real line, here at these isolated points are my positive integers, 1, 2, 3, 4, and so on. 0 is not a positive integer, so I just labeled there at sort of the end. But all along the line in between is this dusting of rational numbers that are not integers. In fact, actually you can prove that between any two rational numbers you pick, there's infinitely many rational numbers. And so the rational numbers are actually packed into this line quite tightly. Another way to think of this is that no matter what real number you pick, you can always find a rational number arbitrarily close to it. And so, to think about why that's true, you can just write down the decimal expansion. And so if you just chop off the decimal expansion at 100 digits, that number is within 10 to the minus 100th of your favorite real number and is rational. So there are all kinds of ways in which, looking at this picture, it would seem like the rational numbers are vastly more numerous than the positive integers. But our intuition has been wrong before. And in fact, if we think about the example we just did, where we looked at the cardinality of the positive integers cross the positive integers, we might realize that it might actually make more sense to compare the set of positive rational numbers to the positive integers cross the positive integers, rather than just to the positive integers. And the reason for that, the reason why I say that might be more natural, is that the rational numbers, remember, are the set of fractions p over q. And so, in a way, every rational number kind of is really just a list of two positive integers. And so maybe what I can do to show you the cardinality of the positive rational numbers is to convince you that the cardinality of the positive rational numbers is in fact actually equal to the cardinality of z plus cross z plus. So, let's try to make that rigorous. Namely, let's show that if you take z plus cross z plus, that ends up having the same cardinality as q plus. Okay, and so both of these cardinalities then are Aleph naught. So, let's prove this. So, Again, we're going to let A be this z plus cross z plus, and B be q plus. And we need to apply Cantor-Bernstein. So to apply Cantor-Bernstein, I really need two pieces. I really need to show you that the size of A is less than or equal to the size of B, and that the size of B is less than or equal to the size of A. So let's do the size of A is less than or equal to the size of B first. So I need to write down a one-to-one function from A to B. What am I going to do? Well, I need to send a pair m comma n to a rational number. Now, I want to note the sort of obvious guess here is to pick m divided by n, but that does not work. Why does that not work? Well, it doesn't work because I don't always get a different rational number. Because, for example, if I pick m to be 2 and n to be 1, I get the same thing as if I take m to be 6 and n to be 3. In other words, 2 divided by 1 is the same as 6 divided by 3. So this function is not one-to-one if I just sent it to m over n. But we can actually borrow our idea from the previous question to write down a fraction that we know is in lowest terms. Namely, what I'm going to write down is 2 to the m divided by 3 to the n. I know this fraction is definitely in lowest terms. How do I know that? Well, if it's not in lowest terms, what does that mean? That means there's a common factor between 2 to the m and 3 to the n. But if you call that factor d that exists in both of these, you could think about what the prime factorization of d would have to be, and then you'd realize that d has to be a power of 2 because it divides the numerator, and has to be a power of 3 because it divides the denominator. But unfortunately, or fortunately, as the case may be, the only number that is both a power of 2 and a power of 3 is 1. So, for very similar reasons relating to the unique factorization of integers into primes, this function is one-to-one. Now, how are we going to show that the size of B is less than or equal to the size of A? Well, one way is to write down a one-to-one function from the positive rational numbers to z plus cross z plus, and I think you can think of a way to do that. But I think it's actually easier to write down the function that we rejected before. So what I'm actually going to show instead is that the size of A is greater than or equal to the size of B, namely I'm going to show that there's an onto function from A to B. And, in fact, that function from A to B is exactly the function we wrote down before. This function is definitely onto. Why? Because every positive rational number looks like a positive integer divided by another positive integer. And so I definitely get out every positive rational number. And so the existence of this onto function and this one-to-one function shows me by Cantor-Bernstein that in fact the positive integers cross the positive integers is a set of the same cardinality of the positive rational numbers. We showed in the previous problem that the cardinality of the positive integers cross the positive integers is Aleph naught, so the cardinality of the positive rational numbers is Aleph naught. Which means that we can go ahead and add the positive rational numbers here. I'll remind you from last time of this bit of vocabulary that we called everything over here countable. And so the way people would usually shorthand the theorems that we've proven so far today is that both z plus cross z plus and q plus are countable. Okay, so let's do one more example. Namely, I want to look at the cardinality of the power set of z plus. Now, in a surprise twist, it turned out that the cardinality of z plus cross z plus, even though that was vastly larger than z plus, was still also the same as z plus, which, again, was probably quite surprising, and probably is something you'll have to think about a lot before you can really wrap your head around it. But now we're looking at the power set of the positive integers. And this is an even bigger set, maybe. Although maybe it will still turn out that it has the same size as the positive integers. What do you think? Do you think this is going to have the same size as the positive integers? Or do you think it's going to have a larger cardinality? In fact, what I'm going to show you is that the power set of z plus has the same size as the closed interval 0, 1, and hence this set is going to have size Aleph C. So here's the first part. I need to show you that the size of A is less than or equal to the size of B. So to do that, I have to give you a one-to-one function from the closed interval 0, 1 to the power set of the positive integers. So the way I'm going to do this is going to be effectively to describe to you how I'm going to encode the decimal representation of a number between 0 and 1 as a subset of the positive integers. So my number between 0 and 1, what's it going to look like? It's going to look like some digit here. Probably that digit is 0, but who knows? It could be exactly the number 1, in which case it would be 1. Point, and then some digit, some digit, some digit. And so these xi's here, these are the digits of my real number. And I'm going to send this to the following subset of the positive integers. Here, again, I'm specifying the decimal digits of the integers I'm now writing down. Just to make this crystal clear, if I take x to be the fractional part of pi, what is my f of x? Well, then my f of x is 9, 90, 901, 9014, 90,141, and so on. Now, actually, I think you can convince yourself the only way for two real numbers to map to the same place under this function is for them to have exactly the same decimal expansion. And there are no two numbers that have the same decimal expansion. And so as a result, this function is one-to-one. Another way to think of this is, if I gave you the set, you could read me back what the real number was. Namely, you find there's only going to be one one-digit number. You look at the two-digit number, and the second digit of that number tells you the first digit, the digit that goes before the decimal point here. Then you look at the only three-digit number. You already know the first two digits, but then the new third digit, that's going to be the first number after the decimal point. Then you find the one four-digit number. You already know x0 and x1, but now the last digit of the one four-digit number in this set tells you the second digit after the decimal point, and so on. And the fact that from an output you can recover the input is another way of saying that the function is one-to-one. Now, you might ask, why did I bother with this business with sticking a 9 at the front? And the only reason why I stuck a 9 at the front was because I wanted to make sure that if the first digit of my number happened to be 0, that it did not just disappear. And so, for example, if I had taken this x, and I'd not put the 9 at the front, then this first term here would have just been 0, and then this term here would have been 1, and I wouldn't have been able to tell the difference between 0.1 and 1.0. So this 9 I've stuck at the front here is actually quite important to making sure that we can tell apart numbers that start with 1 and numbers that start with 0. Okay, now we have to go the other way. I have to show you that the set B is smaller than or equal to the set A. So I'm going to have to show you a one-to-one function from the power set of z plus to the interval 0, 1. So here's what I'm going to do. I'm going to send a set to the sum across all the elements of that set of 1 divided by 10 to that power. Remember, my set B here is just a subset of the positive integers, so this is a sum over just a bunch of integers, and I'm just trying to come up with a number between 0 and 1. And again, I need this to be one-to-one. Now, this might look a little bit messy at first, but actually, once I show you what this function's doing, I think it will be clear what's happening. So let me again do an example, just like we did before, so that we can understand this somewhat complicated function. So let's pick a random subset of the positive integers, or a not-so-random one. I'll pick 2, 3, 5, 7, 11, and so on. This is the set of primes. So what is g of x? Well, it is supposed to be 1 over 10 squared plus 1 over 10 cubed plus 1 over 10 to the 5th plus 1 over 10 to the 7th plus 1 over 10 to the 11th plus and so on, like that. Now, this might seem quite opaque, and you might even worry, what if this series doesn't converge? But I think this actually looks a lot nicer if you think about it in decimal. Namely, this first term here, it's 100th. So it is 0.01. To which I am adding 1,000th, which is 0.001. So there's a 1 here. Now I'm adding a 10,000th, which is 0.00001. So that actually does that. And now actually, if you look at this, what I'm basically doing is I'm putting a 1 in every slot where there was a prime. So 1's not, prime 2 is, 3 is, 4's not, 5 is, 6 isn't, 7 is, 8's not, 9's not, 10's not, 11 is, and so on down the line like that. That's all this sum is really doing. Namely, this is a giant list that tells me what the numbers in the set are. So if I write down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, everywhere there's a 1, those are exactly the things that are in the set. And I have just decided to encode those things that are in the set in the decimal representation of a number between 0 and 1. Now, again, if I started with two different sets, I would get different decimal representations, and hence I would get different numbers. And so this function is 1-to-1. And thus, combining this with the previous part by the Cantor-Bernstein theorem, the size of A and the size of B are equal. And that completes this proof. And so if you come back over here, we can add to our Aleph C bucket the power set of Z+. Again, in the lingo, what we just proved is that the power set of the positive integers is uncountable. But in fact, we proved more. Not only is it uncountable, we showed it's equinumerous with the real numbers or the interval 0, 1, or whatever form, whatever your favorite element here is. One last tiny remark here, just because this is a bit of math culture, because it pops up on social media every once in a while. It is not actually technically the case that every real number has exactly one decimal representation. Some small number of real numbers have two decimal representations. No real number has more than two. Most real numbers have one, a handful have two. And this shows up, and your friends might ask you about it as a math major or whatnot, and the way it shows up in sort of social media and such is that people come across this whole what happens if you take 0.9 repeating. And in fact, 0.9 repeating is exactly equal to 1. Now, a lot of people get very upset by this because they sort of want to say, well, isn't this like 1 minus 0.0 repeating and then a 1 or whatever, but that doesn't actually make sense. And in fact, I think the most convincing way to do this is to say, okay, everyone knows what 0.333 ... is. Namely, that's a third. And so if I multiply this by 3, what happens? Well, on the left I get 1, and on the right I get 0.999 repeating. So I think if you're at a party and you want to impress your friends and they're arguing about this, I think this is the most compelling way to convince them that actually this is true. These are two different ways of writing the decimal representation of the same real number. Now, even though this is true, this does not actually mess up any of our proofs from earlier. And the reason why is this only happens for numbers whose decimal representation ends with an infinite number of 9s. And the only numbers we actually used in our proof here were numbers whose only decimal digits were 0 and 1. So not only did they not contain infinitely many 9s, they didn't contain a single 9. And so as a result, this ends up not being something we have to worry about. But just in case you were worried about it, or just in case your friends ask you, this is a thing you can think about, but it does not actually make this proof fail. All right, we're going to stop there for today. I'm going to do one more video about cardinality, and in that video, I'm going to try and do my best to answer every natural question that this picture might leave for you, but that we have not talked about yet. So, namely, I will answer questions like the following. Is there some in-between set between size Aleph naught and size Aleph C? In other words, could I really have just called this Aleph 1 and been done with it? Or is there something somewhere in between that would prevent that? Also, I'll talk about what happens when you look to the right of this, because as I noted, this is not the last bucket. There's more buckets. And so I'll tell you how to make sets that actually end up in higher buckets than this. That is, some truly preposterously large sets. Again, I'll save that for next time. But that's all for now. I'll see you soon.